All right, well, welcome to the walkthrough of the urban environment chapter. I'm Michelle Stolmacher and I'm at DePaul University. And then we're here today also with Ron Goldblatt. Do you want to introduce yourself, Ron? Or
Yeah, sure. I'm Ron Goldblatt. I'm the Chief Scientist of Neuralite Technologies. My background is in GIS and remote sensing, and I do a lot of work related to urbanization processes and measuring economic activity and economic development in the developing world.
yeah, perfect. All right. Yeah, and when I was first thinking about writing this chapter, I was like, there's no one I'd rather write it with than Ron. So it's exciting to do the walkthrough together too. All right, so the goal of this chapter is to explore several ways to both see urbanization and quantify it from satellite imagery. And we've got a couple of different learning outcomes that we'll walk through today. So creating an animated GIF or GIF, depending on how you pronounce it, and implementing both visual ways of looking at pre-existing urban classifications, as well as quantifying the extent of those pixels. And then Ron's piece will be running classifications of built up land covers where you build the classification yourself, and then using that to quantify and mapping the extent of urbanization across time and space. So we've got a couple of things that it assumes you know from earlier parts and chapters of the book as well. Okay, so I'll run us through section 1 and 2, which is time series animation, where we'll create that GIF of an airport expansion in India, and then section 2, where we'll look at a couple of different urban classifications that exist in Google Earth Engine before I pass it off to Ron for section 3. All right, and then this slide is in every one of our talks, just so you can know how to access the repositories that we're using in the presentation. So you can click on this link, and then if it doesn't show up, there's this refresh button here, and that should allow it to show up. All right, so we'll get right into the practicum part with our various code checkpoints. So the first one that I'll walk us through is this time series animation of an airport being built in India. And then I've got little reminders to myself when it's code demo time. So I'm gonna stop sharing and switch us over to the first checkpoint. All right, so here's our first checkpoint. See if I can make it a little bigger. There we go. And so you can see we're in part A, applications, A1.2, and then this checkpoint A. So the very first step to getting this GIF to run that we saw on the slides is making sure you draw a geometry around that airport in India. So the way I did this is I just searched the name of the city that it's based in. And you can see there's our geometry. And with a satellite-based map, you can draw one that covers the extent of the airport. And we have a modern day satellite-based map here, so you know you'll capture most of it. And then we're centering the code on the geometry here. Oh, and then we're also incorporating our Landsat 8 level 2 collection to tier 1 imagery. And then the very first thing to get our GIF running is to make sure that imagery is the right years that the airport was built in. So we've got our Landsat 8 imagery, we're filtering it by this geometry we drew, and we've got our dates between 2010 and 2020, and then filtering out a good amount of cloud cover. So basically here we're using the metadata of the Landsat image collection to say we only want images that have a cloud cover over land that's 3% or less, because a GIF that has clouds showing up in the cycling of images becomes very hard to understand. So we're pretty stringent with our cloud threshold here. And then the next step is to define the GIF visualization arguments. And some of these are the same ones that you specify when you do map as layer, where you're saying which bands you want visualized and what the min and max of those bands are to determine the stretch But some of these are unique to setting up a GIF, and so that's the frames per second, and this is the speed at which your animation runs. And then we're asking for the format to be a GIF. And then last, to print it out, you do print and then UI.thumbnail, which will print your GIF in the console, and then the collection, which is these images that we featured, and then the parameters. So I'm going to go ahead and hit run, and you'll get your thumbnail generating, and there it is. And so just for curiosity's sake, we could slow this down, maybe do 9 frames per second and hit run again, and you can just see the difference in how the final result looks. All right, so that is checkpoint A, and then I'm gonna do some share screen magic and get us back to the slides. All right, so that GIF gives us a kind of visual look at how this urban area is changing with the building of the airport. But there are a lot of classifications that already label pixels as urban or not, instead of us just visually seeing it with the visual bands. And so these next 3 code checkpoints walk us through some of the pre-existing land cover classifications. And one thing I'll note before I launch into these future checkpoints is that already since the chapter was built, the modus one that's used in the chapter has been superseded by a new one. And so I'm pretty sure the code will work with the new one as well. There's a lot of similarities between the two, but just something to keep an eye on as you're looking at different pieces of code for this book. And then also, since throughout the chapter, a bunch of interesting new urban classifications have emerged as well, like dynamic world and things like that. So this space is always growing and always expanding. So what we're going to do with this first code checkpoint is looking at how urbanization has increased between 2001 modus classification, which we're visualizing in gray, and then the 2019 modus classification, which we're visualizing in red. So this will kind of be the final visualization of the code. All right, so code demo time. Let me switch over again. Oh, no. There we are. Okay, so here is checkpoint B. So you can see we're incorporating the modus land cover type, and this is what I was showing you where the data set has been superseded. So you can just click on that new data set and see the information for that. Okay, but we'll keep going with the depreciated one, since it's a live demo and we don't need to upset the live demo gods. And we're gonna set this over Accra, which is in Ghana. And so we have our map set center there. I'll comment this out and hit run. So now we've set our center over Accra, and then this block of code is visualizing the full classification. So if you look through the documentation for the modus land cover type, you'll notice in the bands that there are actually many different land cover types done by different groups. For example, this one's the IGBP classification. The University of Maryland has a classification. So you have a couple of options even within this one classifier. And so the first thing we do is pick which one we're going to visualize. And so we picked the first one, so modus.select, and then the name of that first land cover type. All right, and then this next part here is setting up the visualization for the land cover types. And this we did not just know off of the top of our heads. These different hex codes to visualize the land cover classes 1 through 17 actually comes from the documentation. So if you click here and then you click see example, you can see the visualization palette that they give in the example. We'll actually run this. So then you know that you have a great palette, the one that's actually recommended by the land cover types here with all of these colors. And you don't have to copy and paste them all yourself into your code. So that's where we got those lines of code from. And then the last step is to just put it all together, map add layer. So we're taking our Modis land cover and we're taking our visualization and putting it on the map. So that's what we've got here for Ghana. As you can see, this gray is our urban extent. But the question is, what year are we looking at when we visualize this? Because we haven't picked a year yet. And so if I click on it, I can see all of the series, all of the images that are part of this visualization. And so we can use this information to help us select the year we're looking at. So that's what we're going to do here with this block of code looking at 2019. And so we've got our original land cover here and then filter date. And the way this is set up here, we know that each classification image is just labeled for January 1st of the year that it's in. And so that's how we know we can just search by date instead of using a date range. So that's how we get 2019. And then to visualize just 2019, we're going to take the 2019 year that we selected, mosaic it to make sure it's a single image instead of an image collection, and then select only the pixels that equal 13. And 13 is our urban pixel. You can see that here in the documentation. All right, so then we're going to do that all again, but for 2001. So we've selected it, we've mosaicked it, and then we're just picking 2013. And then the last thing to do is to visualize the two. And so for 2019, we're taking the image and we're masking it with itself, and then we're giving it a palette. So I think this is going to be the red and this is going to be the gray. I might have it backwards. We'll find out when we run it. And then we're labeling it according to the year. So we've got our two map add layers where we're masking the image with itself, and then we'll see what it looks like. So that gets us that final image we saw in the slides. And we can click on it and see. So our red is the 2019 and our gray is the 2001. All right, and then I'm gonna run through our other two code checkpoints without going back to the slides, and keep an eye out for this. So the way I did the masking here to make it so it's transparent behind, I used a different method in one of the other code checkpoints. So you can see two different ways of doing the same thing. Okay, so that's B. Now we're gonna go to C. All right, so C, we're using Corine, which is from the European Union. So Modis, which we were just looking at, is a global extent, whereas Corine is made by the European Environmental Agency, and so it mostly just covers countries that are in the European Union over these time periods. So the first step is to incorporate it into your code, importing it in, and then we're going to look at London in this example. So we've set our center there. And instead of visualizing Corine like we did for Modis, we're just going to go straight into looking at the individual urban extents. So we're going to first pick 2018, which covers the 2017 to 2018 time period. And we know to filter this from the documentation. We know that the way 2018 is labeled is that it's the first of the year for 2017. So very similar processes to Modis. We've got our classification. We're selecting the land cover band, which is here. And then we're filtering to just 2017 or 2017 and 2018. And then next is taking that we just filtered, mosaicing it, and selecting urban areas. And so here, instead of using an equals to, the EQ, we're using a less than or equals to, and this is because of how the data in Corina is set up. You can see here we've got we start with a bunch of different kinds of artificial surfaces. So 111 all the way through 133, and then 141 starts being vegetated areas, even though it's labeled under artificial surfaces. So that's why we're doing with less than or equals to 133, because we're capturing this all the way through 111. Okay, so that's less than equals to, and then here we're again using the same mask sits with itself. So I guess it's in checkpoint D where we'll see a new way to mask. So there's our 2018 classification, again in red. And then we've got our 2000 classification, and this is all starting to look familiar, so I'll kind of breeze through it, but we're visualizing this one now in gray, and we can see that right over the top. So we see a little bit less growth here in London than we did in Accra, Ghana between 2000 and 2018. All right, so that's C, and then last we have checkpoint D, and here we're looking at NLCD, which is the US's land cover database, and so it's got it for 8 different time periods, and it's got a land cover band, and then it runs you through all of the different land covers here in the documentation. So we've got 4 different developed classes, but one of them is open space. All right, so we'll start again. We're going to center over Chicago, so that's where I'm based, and set it up so we're selecting the NLCD and the land cover band that we just looked at. And then next we're going to filter to 2016, and we're using a different way to filter the dates. I wanted to demo a couple of different options. So this time we're using the system index, which I'll show you. If you look at the inspector, you can see it's one of the properties of an image, the system index. And so we can see that here, it's just the year. It's not the first of the year like we saw for some of the other examples. So that's how I know to filter just to that date. And then the NLCD actually has the visualization already built in. So you'll notice that we didn't specify any visualization parameters here, but we got this very colorful visualization where the different shades of red are our urban classifications. Okay, and then later on in this code, I have us calculating the area of the developed high intensity class in Chicago. And I wanted us to use a true boundary of Chicago, so then we can compare it against maybe the total area of Chicago and make sure our number is correct. So that's why I have us importing this shapefile of the boundary of Chicago. So that way we have that boundary to run our reduced regions over, so we can get a good fact check on our urban extent that we calculate. Okay, so if we're just trying to calculate how much of this area is that dark red high intensity developed class, the first thing we can do is clip that image to that 2016 image just to the boundary of Chicago. And then when I'm calculating areas of pixels, I want everything to be like as perfect and ready to go as possible to make sure that when I run that reduced regions, I'm probably getting the result that I think I'm supposed to be getting. And so that's why I clip the image. And then the second piece is I take those pixels that are class 24, which is our high intensity built up here, the developed high intensity. And I just filtered to those. So I make all of those 1 and everything else 0, because when the reduced region is summing pixels, it ignores the ones that are 0 or masked. And so that way we're focused just on the ones that used to be 24 but are now 1. So that's what we're doing here with this code. We're taking that 2016 image that I clipped just to the boundary of Chicago, and we're selecting only the pixels that equal 24, which is our developed high intensity class. And then here we're using a self mask. So before I was masking the image with itself, but you can do the same thing with this dot self mask function. All right, and then here we have our map add layer looking just at the high intensity areas. And so that's what this layer is here. We'll do a satellite background. So you can see we're only looking at the boundaries of Chicago, and we're only looking at the highest intensity pixels. All right, so then the last thing we have to do once we've got our image in like its perfect shape and optimizing for a good output with our reduced regions is multiplying those pixels by their image area. Because when we do the reduced regions, we're going to sum the pixels, but we don't want to just sum the number of pixels. We want to sum the area of those pixels so we can get the total area of that high intensity class. And so this is our first step to get that area sum. And then we'll do reduced region. We're doing reduced region singular because we're just looking at Chicago. We're not looking at more than one polygon or more than one spatial extent. And then we're using the sum reducer because we're just summing the area of those pixels. And then our geometry is Chicago and our scale is 30. And if you're ever not sure what the scale is for your reduced regions, that is here in the bands usually. Sometimes you'll find it in the description, but you'll often find it somewhere on this page in the documentation. All right, and then we already selected land cover up above here, but just to be extra sure, I'm also saying get land cover here as well. And so when we run this, it'll print the area calculation that we have set up. So here we are. And if you go and Google the size of Chicago, I'm blanking on what it is now. Let's see. I might have this in the slide. You can compare this built up extent, this is in square meters, to the size of the city of Chicago, and you can know that the kind of gut check at that, like this is a smaller number, and it approximately matches what we see visually here. Let me see if I have it on the slide. Oh yeah, here we are. All right, can you all see the slides still? Okay, so yeah, so if everything worked correctly, this is a screenshot from the chapter. You'll see this output. And so we can kind of fact check that with Chicago being around 606 square kilometers. And as a note, if you're ever wondering what the unit is to things printed to the console, it's always the same unit that's used from the image that you did the calculation on. So we know it's in meters, and so that's how we know that this number is in square meters, and it's almost always meters for Google Earth Engine. All right, and then section 2 kind of closes with a couple of questions and things to test your knowledge, and then I also think this is a nice segue to what Ron's going to present, because MODIS, Chlorine, NLCD, even some of the newer land use classifications that have come out since, all have some potential limitations depending on what you're looking for your research question or project. So maybe the pixel size is too great, or maybe there aren't the years available you need, or it's not the kind of coverage that you're looking for. And so that's where what Ron's going to talk about with creating your own classification can be super useful, because you can control all of those parameters, or a lot of those parameters yourself, and get exactly what you need for the time periods that you need. All right, I will turn it over to you.
Yeah, so thank you, Michelle. Let me share my screen. Okay, so as Michelle mentioned, so far in her presentation, we used pre-existing land cover maps of urban areas. What we will do in this section, we will create our own map, our own classified map of urban or built-up areas. We will do it by means of supervised image classification. And we will map the built-up land cover in one city in Ahmedabad, India. But obviously, feel free to run the same code in any city that you want and follow the same steps in any city that you want. What we will do is first we will classify the built-up land cover in Ahmedabad in the year 2020. Then we will classify the built-up land cover in a 2010 image. And lastly, we will estimate which areas were developed between 2010 and 2020, meaning which areas were not built up in 2010, but were built up in 2020. The classification that we will do will be based on Landsat 7 image composite. We will create an image composite for the years 2020 and 2010. And importantly, more theory about supervised image classification you can find in chapter F2.1, Interpreting an Image Classification. So the steps that we will follow are, first of all, we will create an annual composite of Landsat 7 for the year 2020. As I mentioned, we want to predict the class of each pixel in Landsat 7 and predict whether it's built up or not built up. You will find the code to do that in checkpoint A1.2E. Then we will create labeled examples, 100 rectangles or less, of built up and not built up areas. Then we will use the method sample regions to sample the overlapping pixels, the pixels that overlap with these regions that we created in step two, and assign each pixel with a label, whether it's built up or not built up. These will be our training examples for the supervised image classification, because in supervised image classification, we need to have examples with known labels, the labels that we will want to predict their class. Then we will train a classifier. In this case, we will train a random forest classifier, but feel free to experiment with other types of classifiers that are available in Google Earth Engine. Then we will use, once we will have the trained classifier, we will use the trained classifier to predict the class of new pixels in the 2020 Landsat 7 composite that we created. Then we will create a composite for the year 2010. And as I mentioned, we want to identify those areas that have developed between 2010 and 2020, meaning those pixels that changed from not built up to built up. And you can find this code in checkpoint A12H. Okay. So we will start with checkpoint 1.2E. And what I did, I opened a new coding environment, and I will just copy paste the codes from here to this new coding environment and explain what we're doing in each line of the code. So the first thing that we want to do is to search for Landsat 7 image collection. We will search for USGS Landsat 7 level 2 collection 2 tier 1. If you cannot find it here, let's click on more and let's search for Landsat 7 level 2 collection 2 tier 1. I will click on this and we'll click on import, close, and you can see that a new variable was created. Its name is image collection, but let's change it to something more readable. For example, L7, standing for Landsat 7. Again, this is an image collection of Landsat 7 images. What we will do now, we will create a function to calculate surface reflectance. Let me copy this code block, and I will explain what we're doing here. This is a function. This is the name of the function. The function takes each image in the image collection and does something with it. What does this function do? First of all, we are creating masks to mask out cloudy pixels and to mask out saturated pixels. We are using here the QA pixel band and the QA rad sat band to create these masks. Then we are applying the scaling factors to the appropriate bands, meaning to the optical bands. We are selecting from each image all the SRB bands, and from the thermal band, we are selecting the STB6 band. How do we know the scaling factors? If we will click here on the image collection and go to bands, here you can find the scale and the offset. This is how we know the scaling factors that we need to apply. Then what does this function return? It returns the original bands, meaning we are replacing in each image the optical bands with the scaled ones. This is what we're doing here, and applying the two masks that we created here in the function. So this is what this function returns. Now, if I really click run, nothing will happen, because in order for something to happen, first of all, we need to map this function over an image collection. And that's what we will do now. Let me copy this code. I'll paste it here and explain what we're doing here. Here we are defining a new variable called collection. We are taking the L7 image collection from here and filtering it by date. We want to select all the images that were collected between January 2020 and January 21. The result of this is an image collection. Then we map this function that we defined here. The result is a new image collection with all the images that were collected between January 2020 and January 21, where in each image, we replaced the original bands with the scaled ones and applied the mask. So this is an image collection. But as I mentioned, we want to classify the built-up land cover over a single image representing 2020. So this is what we will do here. We are defining a new variable called Landsat 7 2020. We are taking this collection, which we defined here, and calculating a median reducer. If you don't remember what is median reducer, you can also always go to the docs and search for this method. And let's see what this method does. It reduces an image collection by calculating the median of all values at each pixel across the stack of all matching bands. Namely, we have a stack of all the images that were collected between January 2020 and 2021. And for each pixel location, we are calculating the median value of this pixel using all the pixels in the stack of the image collection. So while this was an image collection, the result of this is a single image, an image composite for the year 2020, representing the year of 2020 based on Landsat 7. Lastly, once we have this image, we want to add this image to the map. So we will use the map add layer method. What we want to map is this image, Landsat 7 2020. And here we are defining a few visualization parameters, the red, green, and blue bands. And how do we know which bands are red, green, and blue? You can always look at the metadata at the bands, and we can see that B3 is red, B2 is green, and B1 is blue. We are also defining here the minimum and the maximum of the stretching values of the colors. What I forgot to mention is that in order to do the analysis, as I mentioned, we're classifying the built-up land cover in Ahmedabad. You can search here for the city, Ahmedabad, and it will bring you to the city. What I will do now, I will click here on satellite and uncheck the labels just to see the high resolution image. And now let's click run. And what you will see here, this is an image composite for the year 2020. This is a single image that was calculated using all the images that were collected between these two dates, where we calculated for each pixel its median value. What we will want to do next is in this image composite, we want to predict the class of each pixel. As I mentioned, we are using here supervised image classification. And in supervised image classification, we want to have labeled examples, training examples where each example will have the class of what we want to predict with the input variables, the predictors. We want to train the machine to learn what are the characteristics of a built-up and not built-up pixel. And once the machine learned, we want to predict the class of each pixel in the image. So we need to create our training examples. The first thing that we need to do is give the machine some examples of built-up and not built-up areas. And that's what we will do now. In order to create regions or polygons or rectangles of built-up and not built-up areas, I will click here on this button called Draw a Rectangle. I will click on it, and you can see here that a new variable was created called geometry. Let's change the layer properties of this new layer that we created. First of all, instead of geometry, let's call this layer NBU, standing for not built up. Let's import it not as a geometry, but as a feature collection. This will be a collection of many features where the features will be examples of not built up areas. We will also add a property. Let's add a property called class, and the value will be 0. We can always change the color of these examples that we create to, in this case, I will create it as green. Let's click OK. And now we need to start creating examples of not built up areas. In my case, I'm defining not built up as any land cover that is not built up, whether it's water or vegetation or bare land. Let me uncheck this Landsat 7 2020 image composite that we created. And you can see that the base map that we are looking at here, represent the year 2023. This is a high resolution base map of 2023. We can assume that there's not much difference between 2020 and 23, meaning that most likely many areas have remained the same, whether not built up or built up. This is why in order to create these examples, I will use this base map from 2023. So let's create various examples of not built up areas. We want to select diverse types of land cover, whether it's vegetation, bodies of water, different types of vegetations, different types of bare land. In the checkpoint, in the examples that you will find in the code, we created 100 examples, 50 examples for each class. But for the sake of time, let's create here only 15 examples of not built up areas. You can see here we have 14. Let's create one more example. It's of a not built up area. So now we have this feature collection representing not built up areas, which has 15 features in this feature collection. Let me click on exit. And now what we want to do is create another feature collection, which will have examples of built-up land cover. In order to do this, we will follow the same steps. I will click on New Layer, click here on Edit Layer Properties. In this case, the layer will be called Built-up. We'll import it as a feature collection. We'll click here on Property. Again, we will use the same property class, but in this case, the value that all the features will get is 1, which will stand for built-up land cover. I'm selecting here red. I will click OK. And now we can start creating examples, polygons, rectangles of built-up land cover. Similarly to what we did with the not built-up land cover, we want to select diverse types of built-up land cover or land use, because we want the machine to be able to generalize and to identify all the built-up land cover regardless of the type of the structure or the color of the structure. So let's create 15 examples, and again you can count here the number of examples that we are creating. So far we have 11 examples. We'll select here, select here. This step can be very time consuming, but obviously it is very important because, again, for supervised image classification, we need to have labeled examples of what we want to classify. So now we have 15 examples of not built up polygons or rectangles and 15 examples of built up polygons or rectangles. Let's go now to checkpoint 1 to F, and I will copy this line of code. I will paste it here, and I will explain what this line does. Because here we have one feature collection of not built-up land cover and one feature collection of built-up examples, we want to merge all of them. We want to combine them into a single feature collection. And we will do it using the merge method. So we are taking the not built up feature collection and merging it with the built up feature collection. Just for the sake of the exercise, I can show you that if we will print this new variable that we created, we will get a feature collection with 30 examples, 30 features, because we have 50 not built up and 50 built up. Each feature will have a property called class, which will be either 1 or 0. So now we have these rectangles representing examples, regions of built up and not built up areas. The next thing that we need to do is start building our classifier and classifying the image. So the first thing that we will do, we will define here the inputs to the classifier. In this case, we want to the classifier to look at the bands, at the SRB bands, SRB 1, 2, 3, etc., and use the values, the reflectance in these bands in each pixel in order to predict whether it's built up or not built up. And again, you can go to the metadata, to the bands, and see these are the inputs that we want to use for the classifier, these 7 bands. I'm not selecting, for example, the QA bands because it is likely that the QA pixel band will not differ between built up and not built up land cover, between built up and not built up pixels. This is why I chose here only these 7 bands for the classifier. The next thing that we need to do is create our training examples. What created here that have a class 0 or 1. Our training examples will be pixels because we want to predict whether each pixel is built up or not built up. The training examples are not these rectangles that we created here, but the pixels. For each pixel, we need to know the reflectance in each of the bands and the class, whether this pixel is built up or not built up. So we are defining here a variable called training, for meaning our training example. We will take the image that we created for 2020, select only these bands that we are interested in, and use the sample regions method. What sample regions does, it takes regions and assigns and samples all the pixels that overlap over these 1 or more regions. In this case, we want to sample all the pixels that overlap with these examples that we created and assign to each pixel the class, whether it's 0 or 1. So there are a few arguments that we need to point here. One is the collection that we will be used, the feature collection that we will use to sample the pixels over. The feature collection that we will use is this, the land cover, with the 30 rectangles that we created. Properties is the property that we want to copy from this input from these polygons to the pixel. In this case, we want to copy the property class to the pixels because we want to assign each pixel with a class, whether it's 0 or 1. And the scale, in this case, we're relying on Landsat 7, so the scale will be 30 meters. So these are our training examples. This is a feature collection where each feature is a pixel. And for each pixel, we know the reflectance in each of these 7 bands plus the class, whether it's 1 or 0. So now we have our training examples, and we want to create our classifier that will be used for the classification. So let's define here a variable called classifier. Here in the documentations, you will see that there are many types of classifiers that can be used. In this case, we are using random forest, and I will not get into the theory about what is random forest, what's the difference between random forest, CART, and SVM, but I will say that it's an ensemble of many decision trees. Here we need to define the number of trees in the forest. In this case, I chose 20, but feel free to experiment with different numbers of trees. You can assess the accuracy of your classification, and you will find methods on how to assess the accuracy of your classification in other chapters in the book. So this is the only argument that we will define here in the random forest, which is the number of trees, 20. So now once we define the classifier, we want to train it. We want to train the classifier. The features that we will use for the training are these training examples, which we created here, called training. The class property is the class that we want to predict. For each pixel, we want to predict whether it's built up or not built up, meaning whether the value of the pixel is 1 or 0. And the input properties are the bands. We want the classifier to look at the band values in each pixel, and once it learned what are the characteristics of a built up or not built up pixel, to predict whether a new pixel is built up or not. So these are the arguments that we will define here in the classifier, and the result of this is a trained classifier, where the classifier learned the characteristics of built up and not built up pixels using these examples, training examples that we created. So now we created the classifier, we trained the classifier, and now we want to predict the class of each pixel in our composite. We want to classify the composite. So let's define here a variable classified 20. We want to use the Landsat 7 2020, the image composite that we created for the year 2020. From this image composite, we will select the band and classify it using the trained classifier, which we defined here. If you recall, we assigned a built-up class as 1 and not built-up class as 0. This means that now when we're using the map add layer method, we can mask this layer by itself because we only want to show these pixels that got a value 1, meaning the built-up land cover pixels. We want to mask out or to make transparent all the pixels with a value 0. We'll define here a few visualization parameters and click on Run. Let's zoom out. Let me uncheck this Landsat 7, and you can see that what we are presenting here in orange are all the built-up land cover pixels. Here we used only 30 examples. In the in this here in the checkpoint, we created 100 labeled examples. You can always ask a question, how many examples do you need to create? And again, you want to experiment with different number of examples. On the one hand, you want to have diverse types of examples, but on the other hand, if you want to be able to generalize the classifier to other areas, you don't want the classifier to be too specific. So you don't want to create too many examples. So this is the result of the code that we got here, where we are mapping the class, the predicted class of each pixel in this composite using our training examples and our trained classifier, which we trained based on a few examples of Lancet 7 2020. As I mentioned, the next thing that we want to do, this is the built-up land cover in the year 2020. And now let's say that you're doing a research and you want to identify which areas in this city, in this case Ahmedabad, India, have developed between 2010 and 2020. In order to do that, we need to classify the built-up land cover in 2010. So let's do that. I'm going to checkpoint A1.2H. Let me scroll down. The first thing that we will do, let me copy this code. We will define a new variable called Lancet 7 2010, because this will be an image composite for the year 2010. And we will repeat the same exercises we did previously for 2020. We're taking all this image collection, the L7 image collection, filtering it by date. In this case, we are selecting all the images that were collected between January 2010 and December 2010. We are mapping the same function that we defined here at the beginning and calculating a median reducer. This will result in an image composite representing an image of 2010 based on all the images that were collected between January 2010 and December 2010, where for each pixel we calculated its median value across the stack of the images. Now what we will do, we want to classify this image composite. Now, keep in mind that in this case, we are not creating a new classifier. We are not training a new classifier. What we will do, we will use our trained classifier and we'll try to use this trained classifier, which was trained based on the 2020 image composite, to classify the 2010 image composite. We can assume that the characteristics of built-up and not built-up pixels have not changed dramatically between 2010 and 2020, meaning that we do not need to retrain our classifier. We can use our same classifier that we trained based on 2020 to predict the class of each pixel in 2010. So this is what we're doing in this code block. We're defining a new variable, classified 10. We're taking the image composite for 2010, selecting the same bands that we defined here in this list, and classifying using the same classifier that we defined here, the same random forest classifier that we trained based on the 2020 image. The result of this will be our predicted class of each pixel in the image composite for 2010. I'm sorry, this is what I refer to. Lancet 7 2010, selecting the bands and classifying using the classifier. Similarly to what we did with the 2020 composite classification, Here we will mask the layer by itself because we only want to show those pixels with a value 1, meaning built-up plane cover. I will click on Run, and you will see that now we have an additional layer called built-up 2010, which you will see here in a minute in yellow, representing the predicted class of each pixel in 2010, while the red classification represents the predicted class of each pixel in the image composite of 2020. What we want to do now is just to map those areas that have changed between 2010 and 2020 from not built up to built up. How will we do that? We will calculate here the difference between the 2010 and the 2020 classified image. We're calculating here the difference, taking the classified 20, meaning the our predicted class, our land cover, built-up land cover map for 2020, minus classified 10, meaning our classification for 2010. What are the different options that we will have here? One option is that a pixel was built up in 2020 and not built up in 2010. This is essentially what we want to map. All these pixels that have changed from 0 in 2010 to 1 in 2020. Other options that we have are that a pixel was built up in 2020 and also built up in 2010. And there's another option that a pixel was not built up in 2020 and was not built up in 2010. Obviously, there's another option that the pixel was built up in 2010 and not built up in 2020. But this is unlikely unless buildings were destroyed. So this is what we want to map, this option, meaning that what we want to map are all the pixels with a value 1 in this line, because 1 minus 0 will give you a value 1. So we want to map all these pixels with a value 1, meaning those pixels that have changed from 0 in 2010 to 1 in 2020. And this is the last code block that I will show you. Map add layer. We will take this layer and mask it by itself. Define here some visualization parameters. The name of the layer that will be added here is called difference. Let's click here on run. I will uncheck these layers. And these areas that you see here in blue are those areas that have changed from not built up in 2010 to built up in 2020. So to summarize, what we did here is, first of all, we created an analog composite of Landsat 7 for the year 2020. Then we created labeled examples. In our case, we created 30 labeled examples, rectangles of built up and not built up areas. Then we use the method sample regions to sample all the pixels that overlap with these rectangles that we created and assign each pixel with a class, built up or not built up. We trained a classifier, a random forest classifier. In our case, we used 20 trees. Then we used the trained classifier to predict the class of new pixels in the 2020 composite. We created an annual composite for the year 2010. And in order to identify those areas that have developed between 2010 and 2020, we subtracted the classification in 2010 from the classification in 2020 to map all these areas that have changed from not built up to built up. So that concludes this demonstration and section.